This toy homopolar motor is really cool. You put a wire on the battery, lift up the magnet, put a wire on the magnet. Watch how fast it spins. Today I was going to do some experiments on the toy homopolar motor. Now this consists of a battery, a magnet, a screw, and a piece of wire. So what you do is you take the battery with plus and minus poles and you put one end of it, the minus pole, at the end of the iron screw. That's holding the magnet up in the air. Then you take the wire and you put one side on the positive pole of the battery. The other end of the wire you put on the side of the magnet. And when it puts current into the magnet, it makes the magnet spin fairly fast. That's very well known. It's a very popular toy. It's still spinning because there's a lack of friction. And that's very well known. But what I wanted to do is explore a few unexpected aspects of this toy I found when I began working on it. Now the first unusual thing I found, I had a flathead screw like this, tried various screws, and put that on the magnet, and it worked quite well. But instead, if I used a round head screw like this and tried to put on the magnet, it won't sit in the center of the magnet no matter what you do. So you can't use a round head screw, you have to use a flathead screw. I wonder why that is. The second unusual thing I found, I decided to use a larger magnet, 80mm, instead of this 25mm magnet, and I thought it would work fine. But it might work fine, however, when I put the flathead screw on top of it, watch what happens. The flathead screw wants to jump off. I can't make it sit in the center. And the same thing's true with the round head screw. Also, if we use a very large fishing magnet, which is used to pull bicycles like out of rivers, and we try to put an iron screw on top of it, it likewise just jumps off. After watching all those screws jump away from the centers of magnets, I got some iron ball bearings and put them on magnets to see where the most attraction would be. For small magnets like this little 20mm magnet, you can see the bearings sit just off the center. For this other small magnet, 25mm, like used in the homopolar motor, they again sit just off the center. This is why a round screw won't sit in the center. For a bigger magnet like this 40mm magnet, times 20, they sit around the edges. For a big 80mm magnet, when they jumped off, 80 times 5, they sit around the edges. And for a big fishing magnet, like used to pull bicycles out of the water, they sit around the edges. And the reason is, if you imagine a permanent magnet to be made of lots of circular spinning shapes in the atoms, all of the ones inside cancel. See, the spins cancel, and all you really get are the edge currents inside atoms, which don't cancel. So you only get the edges and not the whole device, and that's why we see these little ball bearings sit on the edges. We can see this very clearly if we use some magnet-sensitive paper. So there's your 80mm magnet and the ball bearings. We'll put the magnet-sensitive paper over it, and you can see an outline around the edges, the magnetism, but not in the center. Likewise for the big fishing magnet, put 6 ball bearings, put the paper over it, and you can see an outline of everything around the outside, including the balls, but not in the center. If we go to the 40mm magnet, again we can see the magnetism around the outside everywhere, but not in the center. Finally, if we look at the 2 small magnets, we can see a ring of magnetism around the whole thing, but the size is too small to resolve the balls. And these things are all consistent with the permanent magnet having all these different loops around it. But only the edge currents are what we're looking at on the paper or when we see the steel balls. Now that we know something more about the physics of the homopolar motor, we can begin to make more sophisticated devices. This one has 2 batteries and 2 magnets. That battery goes up and around down to there. So you go minus plus in series, so you get about 3.5 volts in the circuit. And there's 2 batteries below, each with screws. Now these batteries can be arranged one of 2 ways. They can be arranged with the same orientation or opposite orientations. Now, interestingly, if we have them in opposite orientations like this, north-south, south-north, they'll spin in the same direction. So let's just watch that. Put the 2 wires up here and let's watch them spin in the same direction. The current's going between the 2 magnets of the wire. That's pretty cool, isn't it? Nikola Tesla first did that in about 120 years ago. And I'm just reproducing what he's already done. The current's going around that and then through the wires, and that makes them spin in the same direction because this magnet is north-south and that one is south-north. Now the next way is to have the 2 magnets the same polarity, north-south here and north-south here, which looks like this. Now the 2 magnets are the same polarity, but they spin in opposite directions. Let's watch how that happens. The one on the right goes clockwise, and the one on the left goes counterclockwise as the current goes between the 2 magnets. Very cool, isn't it? And when I remove the power, they'll still spin for a while, but just by momentum. In summary, for this device with 2 batteries and 2 magnets, we can make them spin in the same direction if the magnets are oppositely aligned, or in opposite directions if the magnets are aligned in the same way. If you're a student or a teacher and you want to make this device much more exciting, the best way is to take 4 C-size batteries and just tape them together with electrical tape and put them on a ring stand like if you find in a chemistry lab. And you keep the same magnet with a screw, 20 to 25 millimeter, the same piece of wire. And the 4 C-size batteries will give you 6 volts and 5 amps. It'll be a lot more powerful. Let's see how that works now. Now I've taped one end of that wire to the top of the 4th magnet, and below here I'm hanging the magnet on a 20 to 25 millimeter screw. And let's make a connection, see what happens now with 6 volts, 5 amps. It's very powerful, isn't it? Look at everything sparking. Four batteries gives you a lot more power than 1. Look how fast it's spinning. Now, the lower contact of this wire has to connect a copper brush with the outside center of the permanent magnet like this, or else it won't work. You see it's still spinning very fast. Much better as a teaching demonstration than having just one battery. Now to conclude, I need to say something briefly about how this device works. Each short pulse of current from the brush creates a lens force in the magnet, which causes it to rotate slightly in steps. For example, at time 1, that section of the magnet might get a lens force and it rotates a little. At time 2, the next section gets a lens force and rotates a little more. Time 3, a little more. And there's the brush. Now if we were to fix that brush permanently to the outside of the magnet, we would get continuous current through only one small part of the magnet and it won't rotate. Now it's not that hard to scale this 4-battery device up to spinning larger magnets. Here I've pulled out a very strong 40 times 20 millimeter neodymium magnet. I've just chosen a slightly larger and thicker screw, keep the same piece of wire, and for these 4 batteries what I've done is I've put a little extra piece of iron here to help hold it with a little copper there to make the connection. So we have a really stronger iron connection and it works just fine. Let's see how it works now. Okay, now I've taped one end of the power wire to the top of the 4th battery, the plus terminal. And here's the copper brush down here, the little extra iron with a little copper just stuck in there to make a connection. We take the copper brush, we go to the 40 times 20 magnet and watch what happens. It spins quite quickly. This is quite a strong magnet. Four batteries, a little extra iron, a little bit of copper to make the connection, and we can spin quite a large 20 times 40 millimeter neodymium magnet like a homopolar motor.